Okay, welcome everybody. Let me just get this to slideshow. Ready when you are. Okay, so welcome to week 3 of instrumentation and measurement, where we'll be going into statistics and uncertainty, and also into a bit of random errors, what they mean. So we've dealt with the basics, we've dealt with what we call static errors as opposed to random errors. We dealt with noise and control, and I will start with another summary of what we did in the last week. But today we are going, the interesting bit today will be an uncertainty budget on, I'm not getting you to measure something, but I will pretend to measure something, and the highest sophisticated measurement I will take will be how long is a piece of string. But the idea behind it is to get you to make an uncertainty budget on measuring the length of a piece of string, because there is a lot which can go wrong with it, and we will talk you through that, or I will talk you through that in the uncertainty budget. Before we get to that, we will need to do a bit of a statistics refresher, or new for those of you who haven't done it before. So I'll go into give you a brief review of what we did in last week. I'll go into random errors and some statistics and averaging. I will generally talk about measurement uncertainty, and finish with getting your own uncertainty budget written. So, reviewing from previous weeks, from last week, so somewhere in the notes it may still say that we did random errors last week, but we didn't. They are happening now. We spoke about the systematic errors. We spoke about modifying and interfering inputs. And in systematic errors, we talked about the major sources and what you can do to reduce them. We also talked about interference and sources of interference, how it propagates, remember the conducted versus radiated, and how you can reduce it, how can you prevent and protect against it. We talked about amplifier noise, and the big thing to remember there was at low frequencies you've got the 1/f noise, which decreases with 1/f. Then in the middle you've got the Johnson noise, or Nyquist noise, or thermal noise, whatever you want to call it. And then at the high frequency end you've got the going up shot noise. So remember that little graph that I gave you, that's the important one. And what is signal to noise ratio in amplifiers? I will today talk about signal to noise ratio in a measurement, and they are somewhat different. What they have in common is it's a ratio between the signal to the noise or the error. So while there it was the signal to noise ratio, the one I have today would really rather, I would call it a signal to error or signal to uncertainty, but it's still also called a signal to noise ratio. So be careful between the two of them. And to also talk to you about the noise figure last week. So are there any questions about what we did in previous weeks? If you don't dare to ask now, please come to me in the seminar and ask me tomorrow. Okay? If anything of the last couple of weeks, you have any questions about it, feel free to ask me tomorrow. So today I'll start with random errors, statistics, and averaging. Random errors are the ones you can't, they are not like a bias that you can correct against. They are random, and in their range, do come in, don't stand there. Do come in and find a seat. If you're waiting for a pause, there isn't going to be one for a while. Okay, I shall continue talking. Hopefully the rest of you will be all right. So random errors, they are sort of evenly, from the true value, evenly distributed to the left or right, or not really evenly, but usually on a bell-shaped normal distribution. So hopefully, most likely, you get the right value, but you can get random errors left and right of it. So they are not systematic errors. It's not a bias which is only going one way. They occur both ways. And the way to actually quantify that, since it is usually a Gaussian distribution, we use variance and standard deviation to quantify them. Can I get a show of hand? Who of you knows what is and how to calculate variance and standard deviation? Not many. Yeah, there's the odd hand. Okay. Yeah, I know the faces, so there are people who've been here for a while and they know what it is, because you get it in statistics. But there's too many who don't know, so I shall go through it. And actually for that I go to the workbook. So I go to my .com and I go forward to the page. So here's all the other bit I just spoke about. I shall go to the page about, and yeah, the size is about good. Let me see if anything here is too small. Okay. So the variance is a measure of the energy in the scatter of measurements around the mean value. So what comes in here is the mean value. Xn will be the individual measured value. Xt is that ever elusive true value, and delta n is the error, and I come to that in a moment. So the variance is the scatter around the mean value. So it is actually, if you take xn minus the mean value, you square that, and you sum it over n equals 1 to n for the n number of measurements you're taking, and you have to divide that by n, and all that is what we call sigma squared of x. And just as a reminder how the mean value is found, the mean value is found by doing the 1 over n, so that's an equal the sum of the individual for n equals 1 to capital N. So that's a variance of a measurement. You take the difference between the individual and the mean value, you square it, you sum it up, and you divide by n. The standard deviation is really just the square root of that. So standard deviation is just the square root of it, so it's actually just sigma of x, and you can find it by just taking the square root. Or if you want to go into a bit more detail, it's the root of the mean of the square of the errors. Okay, that's what I've written here. It's the root of the mean of the squares of the errors. So it's equivalent to an RMS value that you may have come across in other words. So your error, that's what we came up above up there. Yeah, it's just about still visible. Your error delta xn is, of course, the difference between your measured value and the true value. But we are actually, in this context, say the error is the difference between the measured value and your mean value. Because we say we've actually averaged over. We don't know what the true value is, but we can find a mean value. And we actually, in this context, define the error as a difference between your individual and the mean. And then your sigma, which equals, the square root of sigma square. You can write this as delta x1 plus delta x2 going on to delta x capital N. They are the errors. You have the squares of the errors, so you square them all. You find the mean of them, so you square them and divide it by n, and you take the root of it. And that's another way of writing the standard deviation as the root of the mean of the squares of the errors, where the errors is xn minus x. And you can, if you want to, actually go into and calculate that out. Okay, now I said we assumed there was no bias. Or we said bias is something different. Bias is something we calculate out. How does bias now come into this? Well, that comes in, and we call this actually the B of x. That is, we are taking our measurement minus our true value. We sum that up for n equals 1 to capital N, and we divide by n. That will be our bias, because if you think about it, you've got a true value somewhere, and if you average out over all your measurements, if you get a difference from the true value, that is a bias. So you can actually also say that this is the same as your mean minus the true value. So the difference between that mean value and your true value will be your bias. Any questions on that so far? If not, I shall go back to the slides. Yeah?
IO or?
Sorry?
Is this BX or IO?
That's B of X, the bias. The bias, B. Yeah? B. Does that look more like a B? Well, a bit. If at any point you can't read my handwriting, please shout out, okay? As reassurance, you will in most cases also, if I go back to the PC now, as I scan through the slides, you see it's all there. All the bits are just handwritten, they're all there. It's just when I write, I can write backwards and show you how the equations are formed. So there you are, the standard deviation and the bias. Okay. So remember, bias is not a random error, and don't confuse the true value with the mean. Although in occasions I will say, I assume there is no bias, I assume the true is the same as the mean, but in general that is not true. I need to specifically say when I assume that. Okay, now I'm doing a bit more on the slides, because if I were to write it, it's a lot of writing, and with my handwriting, God knows. But you still have the workbook. If you want practice, the workbooks on Moodle with all the gaps are there. Take those gaps and see if you can fill them in yourself without looking at the slides. You've always find the full thing on the slides. In this particular case, you also find a full filled-in version, because later on I will be doing something that's not on the slides, but you will have a full filled-in version. Actually, let me show you on Moodle. You have a full filled-in version of the document here. So you've got the workbook with the gaps, you've got a complete version with gaps filled in, and you've got the slides. So several ways of finding, and several formats also, in case whichever format you prefer. Okay. So let's also go back to that. Right, so what happens if we have got multiple measurements, different measurements, and we need to sum them up? What happens to the error if our measurements is not just an x, but we've got an x and a y that we sum? So for a single measurement, we then have, its single measurements is then comprised of an x value and a y value. So two measurements that have been added up together. Then, of course, each of them will have an error attached to it. And that means your total will be the total values, and the errors add up. So that's straightforward. If you've got errors in measurement y and in measurement x, then they add up in measurement z. You may find, if you actually find that the error in measurement y are all negative, they may actually luckily cancel out, but normally they add up. Okay? what does that mean for the variance and the standard deviation? What range of errors would we expect? So I've taken that formula from earlier for the variance, and now taken this equation and put that in there for the individual measurement. And here, as I said earlier, in this case, just to keep the equations easier, I now assume no bias. So I assume that the mean value is the same as the true value, which is why I here wrote minus ZT and not minus the mean value. If you go back a few slides, up here, I had the mean value. I now say I assume the mean value is the true value, there is no bias, therefore I can write ZT in here. Over the next slide, I just I multiply out this squaring, and that happens here. I then arrange things a bit, so I multiply this 2ZT in here, and see things that cancel out. And one thing that cancels out is this part, this is underlined red, and also this and this cancelled out against this. So you're actually left with the deltas, you're left with the errors. What does that mean in brief? I've got my hand speaks on my notes. In brief, that means that the errors of the sums is the sums of the errors. So, particularly if you have two measurements. So what you had here, you have your delta x, your delta y, and you've also got this x times y term. Now that x times y term becomes 0 when the measurements are what we call uncorrelated. If they're independent measurements, if they don't affect each other, then that delta x times delta y can be shown to be 0. I'm not expecting you to show and prove that. What I expect you to know is in an uncorrelated set of measurements, the variance just adds up. So you take the variance of the individual measurement and the sum of the variance is just summing up the variances. So very easy. And that's why I put a star here, because I will refer back to that. That is something we keep referring back to. That if you've got multiple measurements, you add them up, then the variance just adds up as well. Nothing tricky there, it just adds up. Why is that so interesting? That is very interesting because first, before we come to the interesting bit, another point is what happens if we multiply with something? What if we have a scaling factor? So what if your Zn is an a times x? So that will be an a times the true plus a times the error, because xn equals xt plus. Yeah, I'm not quite sure. I need to double check that. Anyhow, whatever might be wrong up here, if any of you can spot what might be wrong. Oh no, it's all right. It's correct, yeah. Because xn is xt plus delta xn. Yeah. My mind had not seen the delta there for a moment. So, because x equals xt plus delta x, your a just multiplies through. If we now want to find the variance, because you squared it all, your a squares. So the variance scales by a factor of a squared. And that down there in bold is the important bit. If you've got a scaling factor of e to a to your measurement, then because the variance is a squared value, that factor a squares as well. I now come to the interesting bit. How can we make use of all this? Right, now let's assume we've got a set of data values. Say you've got a spectrum analyzer that scans through the frequencies and does it again and again and again. or you're looking at a measurement on an oscilloscope and you let it refresh, but as it refreshes, you also let it remember the previous and keep averaging over its measurements sets. What does that do to the variance? Well, so averaging over means we are adding up, we keep adding up. And as I said earlier, a couple of slides earlier, the variance of the sum equals the sum of the variances. So if we take m sets of measurements, then we have m times the variance, because it just adds up m times. Okay? Now, to get the mean, we divide by m. Good. We also learned that we can consider that now a scaling factor. So dividing by m in the linear part means for the variance we need to divide by m squared. So we end up with our variance being the variance of the original divided by m, because from a previous one, okay, so here we had the variance is m times the variance of the individual. Put that in here, we get an m here. We divide it by m squared, so we end up with a sigma squared over m. So now comes this new signal to noise ratio, or signal to standard deviation, actually, ratio. So your signal to standard deviation ratio is V divided by the standard deviation. We found when we average m values, up here we said that is sigma squared over m. So that's the variance of the average. If we now put that into our signal to noise ratio, we will find that the sigma of the standard deviation of the mean is the original standard deviation divided by the square root of m. Putting that back into the signal to noise ratio, we find, just basically plugging things in and forming them around, that our signal to noise ratio now, after averaging, has improved by square root of m. So comparing that back to the original signal to noise ratio where we didn't average, that's just V over sigma, whilst now after averaging over several and taking the mean, we've got the square root of m in there. And that is really the important bit out of here. It's if we average over a lot of measurements, our signal to noise ratio in the measurement improves by a square root of how many often we take this. Why is this important? And for that I just got on the next slide an image. So this is now a time signal that was taken, and it's a very noisy time signal. And if you just measure it once, you don't see anything. You measure it again, you still don't see much, you still don't mean much. After 10 times measuring it, you find features appearing. After 100 times, they're getting clearer. After 1,000 times, you clearly see, oh yeah, there are some little peaks. And that is because those peaks were lost in the noise, but by improving your signal to noise ratio, the noise was reduced, the signal was made clearer, and the signal comes up and is seen. So remember, the signal to noise ratio improved by square root of m. So 100 averages down here improved 10 times, 1,000 average improved by 30 approximately. The downside, the price you pay, is it takes time. And an example in measurements, I used to take a lot, rather than measuring over time, I used to use what's called a spectrum analyzer. I will in a future lecture tell you what that is. It's basically an oscilloscope in the frequency domain. If you know a bit about Fourier analysis, where you can actually have a sine wave or a signal and you show it in the frequency domain, this is a device that measures that. So instead of measuring over time, we measure over frequency. And what that instrument does is it actually sweeps through all the frequencies and takes a measurement. And it takes, I don't know, say a whole sweep over the frequency range you want to look at 10 seconds. So you run through, you get a measurement like this, you don't see anything. You let it run again, you keep letting it averaging until your features build up and you see your features. You actually see the noise floor dropping and you see the features appearing. It's beautiful when you see it and when it happens. But it takes time. So rather than 10 seconds for the scan, if I want to do it 1,000 times, that's 10,000 seconds. That's a bit of time to wait for. If you do that for several things and every time you need to wait till it has averaged out, it builds up. So it takes time, but it's worth it. It's then up to you as an engineer to decide. If I just want to know where those peaks are, and I'm particularly interested in those, the 10 averages have already given me what I need. If I need it much clearer and I also want to find the features back here, which are a lot smaller, I may need to average a lot more. Okay. Any questions about that? Any questions? That's the statistics. That's the boring bit over. As always, if you've got questions tomorrow, let me know. Also, how are we now for time? Yeah, we've only just started. Let me go through the uncertainty and then I offer you a break before we actually do the uncertainty budget, okay? Okay. Right, back to the slides. So what is uncertainty? What does that mean, uncertainty? Well, it's about how sure are you about your measurement result. You have removed all the errors you can think about, you have done all the averaging you can do, but you really should still have an error bar on your measurement. A bit like the picture I showed you I had right at the start, there was a graph with error bars on it. Every measurement should still have an error bar about, yeah, this is a value, but it could be plus minus what? Yeah, I measured 10 volts, but really it could be 9 or it could be 11. And that's where the next bit is, I'm 99% sure it is between 9 and 11. If I want to be 100% sure, I say it's between 5 and 50. Or even there, I'm only 99.9% sure. Yeah? And that's where this little cartoon comes in. There is this weather guy who says tomorrow the temperature will be between 0 and 200. He's got a confidence level of 100%. He is sure it will be between that. But the way he bought that is by having what we call it the margin. He threw in a massive error bar. He has got a massive interval. So yeah, if you draw a massive error bar onto your measurement, you can be sure it is within this error bar. The ideal is to make this error bar as small as possible, but then we need to still state it. We still need to say what our error bar is and how sure are we it falls into it. And that's what the rest of this lecture is about. Okay? So what is the difference between error and uncertainty? So we've defined the random error as a difference between a sample and the mean. The error is the difference between the measured value and the true value. Yeah, delta n minus the average. The uncertainty is a number that tells me how sure am I about that result I'm reporting. It's a bit, there are lots of equations I'm going to throw at you in a bit, but it's not a simple, quick formula about what is the uncertainty. To find the uncertainty, you will need to go through lots of equations and potentially even a spreadsheet. I've got a little sample spreadsheet for simple uncertainty budget on the Moodle page. I will show you later. So yes, we always want to correct, but when we don't know what the error is, when we are not sure about it, we have an uncertainty. Random errors normally normally, usually have a normal distribution. We spoke about them already. You may also have errors which are evenly spread. So for example, if you try to look at a value on a ruler, and we do that later, you've got a finite distribution. Which value on your distribution, between 9.5 and 9.6 millimeter, or between 5 and 6 millimeter, that is more likely to be an even distribution of which values you pick. There are people who argue, no, I'm more likely to get it right, and I'm more likely to be in the middle. It's less likely that I get it totally wrong. There are people who may argue, no, that is Gaussian as well. But there will be things which are clearly the last digit in an instrument. If your instrument has got a digit showing that is totally random, then it's equally, it could be any value between 0 and 9. And that would clearly be a rectangular distribution. There can be other distributions up in the way. You can have something where your distribution is something lopsided, where you say, oh no, it's more likely to give me something bigger than something smaller. You can even have what we call an M-shaped, where you know it usually is plus minus 1. It hardly ever gets the middle. I just want to mention them here. The examples I deal with will all be the Gaussian or the rectangular. And in each case, I will explain why I have chosen that. Okay? But when you as an engineer in the future at some point have to do your own uncertainty budget, you may come across others. I just want them mentioned here. Okay, so before we go into the uncertainty budgets, does anybody want a break, or shall I continue? Anybody want a break? No? Okay, good. Right, let's get into it then. So I go back to our .com. And yeah, we've done this. We've done this. So again, space there for you. The uncertainty budget. How do we calculate the uncertainty of the measurement? And the example I'm doing today is how long is a piece of string? So, could be this piece of string. Could be this piece of string. I'm actually using this one. And I've got different rulers I could use. I've got this. I've got this. All right? So, I'm measuring how long is a piece of string. What do you think? Well, first of all, how would you measure it? What instruments would you use? What would you use to measure a piece of string? I mean, we already had the ruler. Yeah. But it may be longer, it may be a twisted piece of string. Any ideas what you do if it's sort of a twisted piece of string? Tape measure. Okay. So, now, the sources of uncertainty, they can come from different things. So, they can come from the instrument itself. They can come from the thing we're measuring, or they can come from the process, from how we measure. So, if you're thinking about the ruler for now, what could be causing an error that's caused by the ruler itself? Let's think about this thing.
Thickness of the lanes. Thickness of the lanes.
Yeah, the thickness of the lanes. Yeah. So I call that goes in line with the resolution also. So for example, the resolution here is a different one than on this side, isn't it? So yeah, the thickness of the lines and resolution. So yeah, I put this down. Thickness of lines, comma, resolution. Okay? Although you may say, no, they are two different things, can just as equally be argued. Yeah? I mean, this was given to me as a freebie. How do I know it's right? Could be totally wrong. Has it been what I would call calibrated? Have I put it against a known trusted ruler to calibrate that what this calls a centimeter really is a centimeter? Right? So that's what I call calibration. Now, this may have been calibrated ages ago. I once had a beautiful ruler that was made out of metal. Heavy thing, but really good for cutting along and crafting and all sorts of things. But it was made of metal. Could it shrink? If I want to do a precision measurement with a metal ruler, depending on temperature, it could shrink. It should grow. So, has it stretched or shortened? And don't worry, all this, if you can't read, is in the full version. It's all filled in there. So yes, I don't have the thickness of lines in there, so 1.8, I do have the resolution there. The next is possible errors due to the object. Let's start with this one. Possible errors. What could cause errors there? Any ideas? Right, let's show it more on this one. Let's show it more on this one. On this one, it's actually pretty obvious. Let's get closer to the camera. Error in measurement. Where does it start? Where does it end? This has got frayed ends. So actually to define where it starts, yeah, so frayed ends. This one comes down to the similar of measuring. There's a famous thing of how long is the coastline of Britain. And it gets down to how deep do you go into the grooves. So for this one, do you just take the length? Or do you actually go into every little groove and say, I measure every little groove? It will become longer. What you measure is longer than if you just put a ruler next to it. Okay? So, also, if I put it like this, to be rough, and I put the ruler next to it, if I don't put it straight and put a ruler next to it, I also get an error. So, for the string, I would go by, is it straight? And another one is I can pull this up and it becomes longer or shorter. So it could be stretched. I've also got written down here, does the length change with temperature? Just like I did with the ruler, the length of the string could change. But for now I put this, does it stretch? How would you repeatably measure the length of a rubber band? The last dot that we would identify is the measuring process. And the two main things there is in the piece of string would be, yeah, so I've got my ruler and I've got my piece of string and I put it next to each other and I go, yeah, that's about right. Now that's not well aligned. Or where do I find the starting point? So yeah, my starting point is about here. Or if I want to measure the length of this one and I've got this ruler, I need to do here and then from there to there. And you would sort of put it across several times and that will cause errors as well. So they are measurement process errors. So I'd put down here how well aligned a ruler and string. And in most measurement processes, you've got the error of about how repeatable is it. If I measure my piece of string several times, how good is that error? And that actually comes in as the first part of the uncertainty budget when we make it. Okay? So in our building the uncertainty budgets, we've done the hardest bit. We've done the bit of identifying, thinking of, as a homework for tomorrow, think about other things. And talk to me tomorrow and let me know what other things could you think of that could be sources of errors. Okay? The next thing we need to do is we need to estimate the size of the uncertainty. We then need to, and I'll teach you how, combine all those estimates that we get into a single number and then express that as a single number together with what we call the level of confidence. So how sure are you, how confident are you about that? Okay, so no matter what the source of your uncertainty is, there is two types of uncertainties you need to remember, and they are the type A and type B. Type A is the bit about your random errors. That's the bit about your repeatability. And that is really done by, I take repeated readings, and I take an average over the distance from the average, the standard deviation, the variance, gives me actually an uncertainty. That's the easy type A. And the type B is the one that comes from other sources. So the one that you identify as your piece of string, yeah, there is an error from reading it. There is an error from the frayed end. There is an error from the last... I've got an expensive ruler that sent me a calibration certificate. That actually gave me your line are accurate and we've got our own uncertainty budget and tell you what the error of our lines is. So you implement that into your measurement. So your device will have been calibrated. In your second piece of coursework, you will be doing a calibration. The outcome of that calibration is an uncertainty budget. Whenever something is calibrated, you get that uncertainty budget that then somebody who uses that instrument to take a measurement can use for their uncertainties. Manufacturer specifications, calculations, and a lot of experience and common sense. A good instrumentation measurement expert is worth gold in times of when it comes to national standard measurements. The place I worked at, there was somebody who they wouldn't want to let go because he was just so good at taking his measurements. He was so good at knowing potential errors. He was so good at making those budgets that his error margin, his level of confidence was very good and we could trust it. And when it comes to national standards, that is very important. It's a bit like if you think of a starred restaurant. When the chef goes, the restaurant loses a star because it's a chef who knows it. And the same goes with the measurement process. It comes back to the reproducibility I had earlier. What if somebody else takes the measurement? They may take different measurements. They may introduce errors simply because they don't have the experience of what do I need to think about. Do I remember that my instrument needs warming up before I can use it? Things like this. Okay? You can, if you wish, think about type A as random and type B as systematic, but don't confuse them with the expression we had earlier. Okay? The systematic errors we had earlier, they were errors we could do something about, while these are now uncertainties. They are the bits where we say, we've done everything that we can eliminate, this is what's still left. But it does work with, yes, type A. Type A is random. Type A is fairly random as in, okay, so let's take our piece of string. It's really calculated as your sigma divided by the square root of the number of measurements you've taken. So divide your take your measurements, calculate the standard deviation, and divide by square root of the number. So you should be able to calculate, say I've taken 10 measurements. I've already done the bit for you of calculating the standard deviation. So I say I've got a measurement, I've taken 10 measurements, so capital N is 10, and I calculated the standard deviation to be 0.7. What would the type A standard uncertainty be? Now, let me calculate it for you. And I've written it down here. Get out the calculator and tell me if I'm wrong. So, the type A standard uncertainty will be sigma divided by square root of n, which is 0.7 millimeter divided by square root of 10. And hopefully, if you do that, you get 0.2 millimeter. So that will be your type A standard uncertainty that comes out of a standard deviation of 0.7 millimeter. Right. And we park this value. We keep this 0.22 in mind. Actually, let's write it down somewhere as UA, my type A standard uncertainty was 0.2 millimeter. Now, the type B are a bit more tricky, and they go back to the potential errors we identified earlier. And in general, that uncertainty, it's again an uncertainty U, is calculated by, you give it an A, which could be a number, it could be something you've taken from a calibration certificate, it could be, frankly, a number you come up with, it could be a number you estimate, and you divide it by what we call a divisor, and the divisor depends on the distribution of your error. And hopefully that makes a bit sense when I explain it. The divisors, these are the divisors you will need to be able to find. Now, should I ask you this in an exam, I would give you the divisor, and I will not request you to remember those, okay? If I give you this in an exam, I will already tell you what your uncertainty contributions are. You just need to do the calculations. All right? I'm not asking you to decide and identify potential errors. I may have an additional for the final points, just describe to me in a few words what other errors you could think of, and then you just list them. But for them, you don't need to do the calculation. Okay? If you go to past exam papers, you will see examples of that. So let's go to our string example, because hopefully with an example all this makes a lot more sense. All right? And for now, let's also just look at the ruler, because I don't want to look at everything right now. Feel free to yourself add the other bits and make your uncertainty budget bigger with all the other ones you can think of. So for now, I'm just focusing on those three for the ruler. All right? So we looked at the resolution, okay? For that, we need to think about the division on the ruler. So this ruler is divided in millimeters. Now I would say, and that is my judgment, and you are happy to argue with it, but I would say that means my resolution, or the error out of this resolution, is plus minus 0.5 millimeter. And I would say it is rectangular distributed. Because if I want to measure on this ruler, I'm just as likely to say this is 9.45 or 9.48 or 9.40. I think the error between that left or right from that line, is equally, because they are so fine and so close together and the lines are so thick that, yeah, I say that plus minus out by up to 0.5 millimeter, that is equally distributed. That's a rectangular distribution. So I go up in here and say for rectangular distribution, my divisor is square root of 3. So therefore, my uncertainty of the, what shall I give it? I need a nice name. Resolution, URes, is 0.5 millimeter divided by square root of 3, which is, if you type it in, 0.3 millimeter. Okay, so that is your resolution uncertainty. What else did we have? We have has it stretched or shortened? For this example, I say, no, this one probably hasn't stretched or shortened, so I ignore that one. If I were to write a full report, I would actually make a statement to say that I do not consider that a significant error. I would actually have to state, even the things I said I'm not taking into account, I would have to state what I didn't take into account. So anybody who sees my measurement report knows that, okay, was taken into account, not something that was forgotten, but was considered negligible. And the last one we had was the calibration. And here I just come up with, in the book I've written, so this ruler had a data sheet, and the data sheet tells me that it has been calibrated with an uncertainty of 0.1 millimeter. And they also told me that it was with an 0.1 millimeter with a coverage factor of 2. And we come to the coverage factor in a moment, okay? So the calibration certificate says, yeah, our calibration uncertainty is 0.1 millimeter with a coverage factor of 2. So you go back up into the table and find your divisor, so that is then 2. You need to divide back by that coverage factor. So you say, therefore, okay, my UCal, my calibration uncertainty, is 0.1 millimeter divided by 2, and that is 0.05 millimeter. Okay. Now there are more, but just for the exercise, just deal with those and see how would we now report all this and how would we put them together. So we have, and let's put that there. So we had UA was 0.2 millimeter. Then we have our resolution, and that was. I actually write it like this: 0.5 millimeter divided by square root of 3, and the calibration, and that was 0.3 millimeter. Because the spreadsheet I'm giving you does that already for you as well. And the calibration would be 0.1 millimeter divided by 2, equals 0.05. Okay, good. Right, so all those values are now there, so I can turn the page. How do we combine them? So, we had our type A being UA equals 0.2 millimeter. And what we call type B, they are all of the measurement, anything that is not random from multiple is type B. So we had type B resolution, U res equals 0.3 millimeter, and calibration U cal equals 0.05 millimeter. Your combined standard uncertainty, UC, is the root of the sum of the squares of each of them. So you take in millimeter 0.2 squared plus 0.3 squared plus 0.05 squared, and take the square root of all that. If you type that in, you get to 0.36 millimeter. That is your combined uncertainty, UC. Now we spoke earlier about the level of confidence. And how do you, what an expanded range, the wider you go in your uncertainty, the more is your confidence level. The higher is your confidence that it really lies within that. Now, I would say I'm not really confident with those 0.36. A lot of guesswork went in. I'm really not confident with this. So just to be on the safe side, I multiply that by 2. And that's what we call that coverage factor. That's what the guys who calibrated the ruler did. They say, I use a coverage factor of 2 to get a higher confidence level. And there are tables you can find, and these are general accepted tables. They are standardized tables where you go to get a confidence level of 95%, which is the most common, you multiply by 2. Sometimes you want to get better and you multiply by higher values. So the bigger then your uncertainty margin becomes, the higher becomes your confidence level in it. So usually we use a confidence level of 2, which leads to an uncertainty, to a confidence level of 95. So we would then say our combined would be 0.72 millimeter in our case. And I have on the last page, but it's a bit small here, and I go for that. I think I've got it on here. No, I don't. I have in the full version, I have a scan of. This is the point where I tell you about the spreadsheet. So, down here is a spreadsheet. Oh, come on, PC. Down here is a spreadsheet, uncertainty budget spreadsheets, which then I open that. There is a sheet which is free where you can play around and add your own lines and do other things. But sheet 2 is where I've actually filled something in. Okay? I've got slightly different values here. Oh yes, a rectangular resolution, yes. So instead of square root of 3, I've got a 1.73 here. And you actually see what that leads to. So those numbers we had down there, you find in here. Oh, let's make that bigger so you can actually see it. So I've got I typed in my 0.2, I typed that in here. A uncertainty of 10 repeated readings, that was my repetition, that was my type A uncertainty. They are usually normal distributions, therefore, and they are normal distribution with a divisor of 1. Your type A are always like that, so that number filters straight through here. I did not type that in. The resolution, we said that was 0.5 and it was rectangular. So I typed in the 0.5 and I typed in the 1.73. Well, actually I set square root of 3 up here. And it came up with 0.29 by dividing B3 by D3. If you can see this up here. Okay. So that did that for me, just with a higher accuracy than I did here. And for the combined standard uncertainty, it actually then does the square root of the squares for you. So it combines them all for you. And if I now say, yep, I want a 95%, I add a divisor, I add a k, and it then says, yep. It has, you can clearly see it has carried more digit than it actually shows me, which is also quite interesting when you use spreadsheets. Yeah. So in the one I've actually printed in the, when you look into the document where everything is together, I've slightly fudged and corrected them. Moodle. So if you go into the completed workbook, onto the last page. So there you see what happens with error bars, and right at the end, here I have shown you how I would present that. Make that big so you can see it. So this is how you would present this. It is actually usually presented as a table or a spreadsheet, because that way whoever you give this to, they can see the whole spreadsheet. Now if this is an exam question, I will not expect you to produce a spreadsheet for me in an exam, because you haven't got the technology. So I'm afraid in an exam you need to do the working out by hand that I did before here. So in an exam I would expect you to do these calculations and calculate them for me. Do not forget when you combine them the type A. Common mistake when you combine them all. If I asked you to calculate the type A, I asked you to calculate a type B, I asked you to combine them all, you add up all the type B's one and forget the type A. It's the most common mistake in there. So you've heard it here, don't do that. And I will then ask you to give me the result in this form. So for me, earlier on I may have told you I measured 19.9 centimeter. That 0.72 millimeter you can round to 0.07, because considering it is in centimeter, it makes sense if you report in centimeter. It depends. If you are wanting to report on a precision resistor, that needs to be a precision 1 kilo ohm resistor, you may want to present the uncertainty in ohms rather than in kilo ohms. It really depends on what you need, okay? So I will not penalize you on you rounded that slightly wrong, because that comes with judgment and your application. But what you need to have in there is what was the length you measured, and that would have been the mean value of your measurements, plus minus whatever you ended up down here, and stating that you used what coverage factor did you use and what is your level of confidence due to that coverage factor. That is how you do an uncertainty budget. So all that's left to me, and I will be open for questions in a moment, is there are a couple of books on the list. on how to measure uncertainties. So there are a few that you can actually find in the library or online, but I've also put you on Moodle, should you wish to look more, find more about that. Oh yeah, a beginner's guide to uncertainty and measurement, which is where I, to be honest with you, this is a colleague of mine back when I was at the National Physics Laboratory, and she wrote this guide, and it's a brilliant guide. So the idea of measuring a piece of string was actually hers, so I have to give her full credit there. And you will find in here measuring the length of a piece of string in a lot more detail, okay? And a lot more detail on other things. So if you want to learn more about this in more detail, Stephanie's work is brilliant. I can only recommend it. So she talks a bit more about averaging and spreading, so really good. Other types of measurements, how you get a mean. Okay, and what I would call if you become a serious metrologist, as we call ourselves, the expression of uncertainty and confidence in measurement, this is the eased down version of a legal government document. And this is in its all glories of more than 80 pages. This is the guide to the legal document. With examples and explanations. So if you want to read how legal people and how the United Kingdom Accreditation Services expresses uncertainty, they are those we all bow to, and we all have to get our measurements approved by in the end if we work in an accredited test lab. So different UCAS than you might know. When I came here, to me UCAS meant something totally different than what it meant to our students. They've got an introduction which reads very legal, but what they have, and you may want to look at it, they have lots of examples. So some sources of error and uncertainty in an electrical calibration, environmental conditions, calibration data, resolution we talked about, how is your measurement set up? If you do a sensitive measurement using a spectrum analyzer or a network analyzer, you actually need to calibrate your cables, because how you move the cables can change your measurement. Thermoelectric effects, cable impedance. If you're measuring with a cable, the impedance of the cable you're measuring with can affect your measurement. Needs to be in your uncertainty budget. What if you do high frequency measurements? Lots of things can go quite interesting, and lots of statistics in there. So if you want more examples of what do people who really get into measurements have to look out for, only then look at that document. If you just want a bit more guidance, have a look at Stephanie's. Or as always, feel free to ask me tomorrow. So my homework for you tomorrow, again, there's in the question sheet. My homework for you for tomorrow is not necessarily do, because there's only a day left, but have a think about what else would you put in your uncertainty budget for your piece of string. What are you not sure about? What kind of resolution, what kind of distribution would that be? Happy to discuss all that tomorrow. Okay? I shall stop the recording, and then I'm happy to answer any more questions.